Now, wait a minute. Finish it. A third of the
All right. So we're going to talk today about vector valued functions. It sounds a little intimidating, but it's really nothing that we haven't seen before. We're just going to kind of take what we know in a little bit different direction. No pun intended, right? Maybe just a little. Okay, and let's see. Nicole? What was the name of that? What was the software that was on the new Apple computers? So this semester, if you have that 3D graphing capability on your computers, and I'll show you some other resources for that. It's going to come in very, very handy. So what we're going to do is today we're going to extend what we know about parametric equations. So we've used parametric equations to describe a curve in the plane. So for example, if we did some work when we had our parameter as time, and we said that we did a lot of work with parametric equations where x was some f of t and y is some other g of t, and this gives us coordinates in the plane that describe a curve as t varies. We also talked about polar coordinates. We could think of polar coordinates as parametric equations where our angle, we could talk about our function of r and theta. So we get a position based on our radius and our angle. We can extend this idea to 3 dimensions. We did a little bit of, well, we talked a little bit about motion in the plane with parametric equations. We can extend it to 3 dimensions. So we could say extend it to 3 dimensions, and we say z is some other function of t, and this gives us the coordinates of a point in space. So this is just kind of a quick recap of what we did with parametric equations. We can also think of these coordinates as the components of a position vector. I could say, we say could or can be. So we say that r of t, and we usually use r for a position vector. R of t is f of t I hat plus g of t j hat plus h of t k hat. And the tip of this position vector traces out a curve in space as t varies, and this should have a vector sign over it. So the tip of this position vector traces out the curve as t varies. So rather than coordinates, we get a position vector. So this is what we call a vector valued function. We plug in, our domain is some set of scalars, and we get out a vector. For each scalar, each value of t, we get out a vector. So that's what we call a vector valued function. And just to draw a little picture of what we're talking about here, if we draw a little coordinate system, we'll be drawing lots of pictures this semester. To me, that's what makes part of what makes this fun. is that it's so visual. So visual, that's right. I'll make the vectors red. So if we have these vectors, and I'll call this R of T1, R of T2, and R of T3. And we get this curve as R varies, connecting the tips of those position vectors. And this is our curve C. So as the position vector changes, we get this curve, and if we project this down into the XY plane, I'll just say maybe this projects onto the x-axis, maybe this projects down here, and this projects down here, and it traces it all. If we project this down, we get a little curve in the XY plane as well. So we could project that onto our coordinate planes to get an idea of what the curve does. So we call R of t a vector valued function. It's our basic idea for this chapter. And the component functions are f, g, and h. We call f, g, and h component functions. Our parameter is t. And the domain of R, the domain of our vector valued function, is the intersections of the domains of f, g, and h. So what I want to do today is, one, just introduce this idea. So we're just taking parametric equations, really, and turning parametric equations into vectors. That's really all we're doing. What I want to do is practice a little bit on visualizing, practice a little bit with visualizing what these vector valued functions, what different vector valued functions would look like. So that's going to be a pretty big part of what we do this semester is work on the ability to visualize these things in 3 dimensions. So let me grab, I have some graphs and some equations, and I want to match these up. So let me grab the equations. I want to go back. That. I wanted to put this in the page. So there are our equations. Let me grab our graphs, and we're going to match these. We want to match these up. So there we go. We want to match these equations to the graphs. So what we want to do with these vector valued functions is similar to what we did when we talked about surfaces in the last chapter. We want to think about a relationship between the coordinates to decide what is this going to look like in one of the coordinate planes. If we project the curve onto one of the coordinate planes, what are we going to get? So let's look at this first one. What relationships do you see there between the components of that vector that look like they could be useful? What do you think, Matt?
It's linear between I and J.
It's linear between I and j. So in the xy plane, if we projected this curve down onto the xy plane, we would get a line. So just looking at these and so let's go one step further before we decide which curve this is. What other relationship could be useful?
The YZ relationship.
The YZ relationship, and what's going to be that YZ relationship between the components?
A parabola.
A parabola. So in the YZ plane, we need a parabola. So in the XY plane, we get a line. YZ plane, we get a parabola. So which curve is that going to be?
B.
That's going to be B. So we get a parabola in the YZ plane, a line in the XY plane, and what do we have in the XZ plane as well? Parabola. A skinny parabola. So what I did here is I made one of these that we can actually move around. So there's our function graphed in 3 dimensions, and so let's see. The XY plane is down here. The origin is at the center of the box. So there's our parabola in the XY plane, or sorry, XZ plane. And let me see if I can turn it the right direction. Sometimes it's hard to figure out how to turn this. There we go. And there we go. In the YZ plane, we get a parabola. And if we look at it straight above, there's our line in the XY plane. And I couldn't figure out last night how to do it takes a little more work to do a little shading below that curve, and I couldn't figure out how to do it quickly last night. But I'll get back. I have lots of these graphs that we use this semester. So there's what this looks like if we rotate it around in 3 dimensions. And hopefully what we get to the point where we can kind of visualize, and you can do that in your head. And it's kind of a fun thing. All right, let's look at the next one. So this is our vector valued function cosine pi t I, sine pi t j, and t squared k. So I'm hearing C, C, C. What tells us that it's going to be C? Sines and cosines. So in the xy plane we have sine pi t and cosine pi t. So x squared plus y squared equals 1. So we get a circle in the xy plane. And the only one that has a circle in the xy plane is C. So this is going to be B, and this one's going to be C. And then we have this kind of quadratic relationship in the xz and the yz plane. We get this kind of thing going on. So let's look at that one that we can move around. So there's that curve. So if we look at it from above, there's our circle in the xy plane, and then we get this kind of interesting quadratic thing happening in the xz plane, and then if we look at it this way, kind of a nice little shape there. Interesting things happen with vector value functions. You can get some interesting curves. Oh, and I was going to point out, this is one way, a pretty easy way to, we talked about a little bit last semester, rotate axes. So here's a parabola with a rotated axis. It's rotated off the xy or the yz, or this one representing it as a vector value function is a way to rotate axes kind of less painfully than other ways that you do it. All right, how about number 3? So we have between the xy plane, we're going to have a what kind of shape?
Parabola.
Parabola. And then we also have this exponential thing between the x, z, and the yz. So which one, just looking at these, which one is going to give us a parabola in the xy plane? D. This looks like it could eventually, but it's not quite, not really. So this one's going to be D. We get a parabola in the xy plane, and we get this exponential thing happening in the xz plane. So let's look at that one where we can rotate it around a little bit. So there's our, let me get this set up. There we go. So here's our curve. Let me rotate it around the way we normally do. Something like that is the way that it's drawn on the page there. So if we turn it here, look down on the xy plane, there's our parabola. And if we turn it this way, and I line it up just right, oops, what did I do? Trying to rotate it around so we can see that exponential thing. There we go. And there's our exponential curve in the xz plane. And then in the yz plane we have another interesting thing happening. All right, so that one was D. So that leaves us with A for the last one. So we have a logarithmic curve in the xy plane. So there's our logarithmic curve, and then we end up with a line in the xz plane for this one. So let's take a look at that one. So there's our line, and then there's our logarithmic function. So we rotate it this way, we get a line. There's a logarithmic function in the other plane, and then we come around this way, and we can see how it curves up. So tonight's homework really is about visualizing these curves, and also looking at the domains a little bit. But really, what I want to do is kind of just a gentle introduction, and give us some tools for visualizing these vector value functions. So really, what we want to do, what you want to think about is what are they? If you look at the projection in the coordinate planes, what kind of shape, familiar shape, does that give you? And then you put those together to get a picture of your function. Questions? Okay. Nice, gentle introduction for our first day back. All right, homework.
I love this book.